October 14, 1940, a moonless night over the English Channel. The air inside the Bristol Beaufighter's cockpit smells of oil and sweat. Flight Lieutenant John Cunningham adjusts his grip on the throttle, two levers controlling two engines that aren't supposed to exist. Below, the Luftwaffe's Heinkel bombers drone toward London, invisible in the darkness. Cunningham's aircraft accelerates, the twin Bristol Hercules engines producing a sound unlike anything else in the sky, a deep mechanical growl, smooth as rolling thunder. No vibration, no misfiring, just 3,200 horsepower of pure, relentless thrust. In 8 minutes, he'll intercept a bomber that Germany thought was untouchable. The engine that makes this possible was called a failure by every aviation expert who saw it. The man who built it was about to prove them catastrophically wrong. To understand why this moment mattered, we need to go back 17 years, to a drafting table in Bristol, where Roy Fedden was staring at a problem everyone else had accepted. Aircraft engines of the 1920s used poppet valves, metal mushrooms that popped up and down thousands of times per minute, opening and closing ports to let fuel in and exhaust out. They worked, but they vibrated, they overheated, they failed in dust. They couldn't handle the power demands of modern warfare. And Roy Fedden, chief engineer of the Bristol Aeroplane Company's engine division, refused to accept acceptable. The sleeve valve concept wasn't new, a thin metal sleeve sliding up and down around the piston, with ports that aligned to control airflow. Smoother, more efficient, theoretically capable of higher power outputs without the mechanical violence of poppet valves hammering thousands of times per minute. But every major manufacturer had tried and failed. The sleeves seized, the tolerances were impossibly tight, 1/1000th of an inch too loose and compression escaped, 1/1000th too tight and friction welded metal to metal at operating temperature. Rolls-Royce had abandoned the concept in 1928. The Air Ministry's engineers called it mechanically suicidal. Roy Fedden called it the future. He was born in 1885 in Bristol, apprenticed in engineering at 16, and learned aircraft design during the First World War when engines failed so often that pilots expected it. By 1920, he was running Bristol's engine program, and he had a reputation. Brilliant, yes, but abrasive. He didn't suggest improvements, he demanded them. He didn't negotiate with bureaucrats, he lectured them. He believed engineering problems had engineering solutions, and politics was what incompetent people used when they couldn't solve problems. This belief would power a revolution. It would also destroy him. Between 1925 and 1933, Fedden's team built 14 prototype sleeve valve engines, 11 seized during testing, 2 melted their cylinder heads, 1 exploded on the test stand, sending a piston through the roof of the workshop. The Air Ministry refused funding 3 times. Rolls-Royce engineers published papers explaining why sleeve valves would never work in high-performance applications. Bristol's board of directors asked Fedden, politely at first, to abandon the project and focus on conventional designs. He ignored them. He personally designed a lubrication system that fed microscopic amounts of oil between sleeve and cylinder wall, enough to prevent seizing, little enough to avoid fouling spark plugs. He specified cylinder materials, steel alloys that expanded at precisely matching rates when heated to 400 degrees Celsius. He hired machinists who could hold tolerances to 0.0005 inches, then trained them to hold 0.0003. And in 1933, the Bristol Perseus ran for 100 hours without failure. It was producing 800 horsepower, 30% more than any poppet valve engine of equivalent size, and it ran glass smooth, with vibration levels so low you could balance a coin on the casing. The Air Ministry was unimpressed. Impressive in a laboratory, they said, but combat conditions would destroy it. Dust would clog the sleeves, tropical heat would cause expansion seizure, battle damage would jam the mechanism. Stick with Rolls-Royce Merlins, proven, reliable, understood. Fedden's response was to design a bigger engine, the Bristol Hercules. 14 cylinders arranged in 2 rows of 7, each cylinder containing a sleeve valve sliding through a cycle 2,000 times per minute. First run, February 1936. Output, 1,290 horsepower. By 1938, with supercharging refinements, 1,680 horsepower. And here's what the skeptics missed. The smoothness wasn't just pleasant, it was structural. Poppet valves hammered. That hammering cracked engine mounts, fractured fuel lines, fatigued airframe attachment points. Hercules engines didn't hammer, they purred. Aircraft built around them could be lighter because they didn't need to absorb constant vibration. Lighter meant faster, more maneuverable, longer range. And this is where the story takes a turn no one expected. But before we get to that, if you're finding this untold history as fascinating as I am, drop a comment below. Which World War II innovation do you think changed the war most? And hit that like button. It tells YouTube to recommend this to more history lovers like you. September 1939, Germany invades Poland, Britain declares war, and suddenly the Air Ministry needs night fighters, aircraft that can hunt bombers in total darkness. The problem, existing fighters can't carry the weight. Airborne radar equipment weighs 600 pounds. Heavy cannon armament adds another 800 pounds. Most fighter designs can't handle the load without sacrificing speed and climb rate. But the Bristol Beaufighter, designed around 2 Hercules engines, can. It's fast, 330 miles per hour. It's armed, 4 20mm cannon plus 6 machine guns, and it's stable enough to mount radar without vibration ruining the display. October 1940. First operational Beaufighter squadron forms. Luftwaffe bomber crews are told they're safe at night. British fighters can't find them, can't catch them. Then John Cunningham, soon to be nicknamed Cat's Eyes by a public that doesn't know about radar, starts shooting them down. First kill, October 19. A Junkers 88, intercepted over the channel, hit by cannon fire that tears through a fuselage like paper. The crew never saw the Beaufighter coming, never heard it over their own engines, just sudden impacts and fire. By December 1940, Beaufighters are downing German bombers at a rate of 12 per week. Luftwaffe intelligence is baffled. How are the British finding them? How are they catching aircraft that should be faster? They blame spies, impossible radar ranges, even rumors of British pilots with surgically enhanced night vision. The truth is simpler. Roy Fedden's engine works in cold, in damp, in the vibration-heavy environment of combat flying. Hercules engines run 400-hour overhaul intervals while Merlins are coming off at 250 hours. When Beaufighters deployed to North Africa in 1941, flying through sandstorms that choke Spitfire and Hurricane engines, Hercules engines keep running. Filters clog, maintenance crews clean them, engines restart. No seizures, no mystery failures. By 1943, Hercules engines are powering more than just Beaufighters. Short Stirling heavy bombers, 1,760 of them built, each carrying 4 Hercules XII engines, lifting 70,000-pound aircraft to 17,000 feet to drop bombs on Berlin. Lancaster bombers, the Pathfinder variants that mark targets for bomber streams, use Hercules engines because they're more reliable than Merlins in the temperature extremes above 20,000 feet. Halifax bombers switch from Merlins to Hercules engines mid-production because operational squadrons demand them. Mechanics in the field report what engineers predicted. Sleeve valve engines don't care about conditions. They run in Norwegian cold that freezes poppet valves shut. They run in Burmese heat that warps cylinder heads. They run when they shouldn't, because Roy Fedden built them with obsessive precision that most engineers thought was unnecessary. Here's something most documentaries won't tell you. Fedden's success made him enemies, not among pilots or mechanics, but among the bureaucrats and rival manufacturers who'd spent years explaining why his ideas wouldn't work. Rolls-Royce, Britain's aviation aristocracy, hated that a Bristol engine was outperforming their Merlins in reliability metrics. The Ministry of Aircraft Production, reorganized in 1940 under Lord Beaverbrook, hated that Fedden wouldn't simplify his designs for mass production. He insisted on precision. He rejected cost-cutting measures. He fought every attempt to dilute specifications. And in the politics of wartime production, fighting is fatal. Fedden is called to the ministry. The meeting is polite. His contributions are acknowledged. His engines are praised. Then comes the request. step aside. Let someone else manage production scaling. Someone more cooperative. Someone who understands wartime necessities. Fedden refuses. He's told it's not a request. By August 1942, Roy Fedden is removed from operational control of Bristol's engine division, the company he built from a small workshop into Britain's second-largest aero engine manufacturer. The engines still carry his design DNA. Every Hercules built until 1945 uses his sleeve valve architecture, his lubrication system, his material specifications, but his name disappears from reports. Credit shifts to committees, production managers, ministry officials who've never held a micrometer. It's impossible to hear these stories without feeling something. Anger, awe, sadness, all of it. Let me know in the comments how you're processing this, and if you believe these forgotten engineers deserve to be remembered, that like button is how we make sure their stories don't disappear. Fedden spends the rest of the war consulting. He advises on engine development. He writes technical papers. He tours factories where workers build engines he designed under supervision of men who couldn't have designed a lawnmower engine. He watches, from the outside, as Hercules engines power 57,400 aircraft sorties in 1944 alone. He attends ceremonies where ministry officials receive awards for aviation production achievements built on his innovations. He is polite. He is professional. Internally, he's dying. Post-war, there are honors. A knighthood in 1945, Sir Roy Fedden, for services to aviation. Membership in engineering societies. Occasional lectures where old engineers nod and young engineers have never heard of him. He publishes a memoir in 1956. Fewer than 2,000 copies sell. Rolls-Royce, by contrast, is celebrated globally. The Merlin engine becomes synonymous with British aviation excellence, powering Spitfires and Hurricanes in popular memory. That Hercules engines were more reliable, more powerful in larger aircraft, more versatile across climates, these are footnotes in official histories. Roy Fedden dies in 1973, age 88, at his home in Gloucestershire. The obituaries are respectful but brief. Pioneer of sleeve valve engine design, contributed to Britain's air superiority. The BBC runs a 90-second segment. Rolls-Royce executives who met him once send flowers. The mechanics who serviced Hercules engines in the desert. The pilots who flew Beaufighters through flak over Hamburg. The engineers who learned precision tolerance from his training programs. They remember, but memory fades, archives close, and within a generation, Roy Fedden becomes a name in technical journals, unknown to the public that flew safely because of engines he refused to compromise. Here's the final truth. Engineering and politics are both forms of power. Engineering shapes what's possible. Politics shapes who gets remembered. Fedden mastered one and dismissed the other. He built engines that won battles, but lost the bureaucratic wars that decide legacy. He proved the experts wrong, but couldn't prove himself agreeable. And in the end, Britain's night skies were defended by his genius and cleared by his stubbornness, one quality saving lives, the other erasing his name. This is just one inventor story. There are dozens more. Engineers who built the Merlin supercharger, the cavity magnetron radar, the Whittle jet engine, names history forgot, machines that shaped the world. I've got their stories ready for you. The next video covers Barnes-Wallis and the bouncing bomb that shouldn't have worked. And trust me, that one will change how you see engineering under impossible deadlines. Click that subscribe button, hit the notification bell, and I'll see you in the next one. The engineer who fought everyone, the engine that never failed, the legacy that flew unnoticed into history.